Welcome to our webinar. Today we're going to make a journey into Freedom Space 4.0 of 142 billion molecules. My name is Olga Tarhanova. I'm CEO of ChemSpace, and I'm pleased to host today's webinar for you. Before we start, a few organizing moments. I would like to let you know that all attendees will be on mute while the webinar, and the chat box will be also disabled. But you have access to Q&A section, and actually you can use this section while our Q&A session. Another moment, organizing moment, this webinar is being recorded, and the record will be accessible through the link on our YouTube channel. Okay, I think we could start, and we will start with overview of the agenda for today. So today we will present you a new combinatorial space, which is called Freedom Space, the newest version of this space, which is 142 billion molecules. We also talk a little bit about possibilities to generate so-called custom spaces using our quite unique approach. And then we will talk about how to explore such a huge chemical spaces, and the Freedom Space 4.0 is an example of quite large chemical space. So we will conclude with the Q&A section, and as I mentioned, you may type your questions in the Q&A section, and then I will read and the speakers will address the questions. So we have two speakers for today, me, and I will be talking about Freedom Space and custom space generation. And it's a great honor to introduce you David Cosgrove. He is a cheminformatics developer. He spent 28 years working in pharmaceutical industry, mostly in AstraZeneca. He got his master's in chemical informatics in Sheffield University and his PhD in computer-aided drug design in Leeds University. And since 2016, he is a freelancer. He's working with such customers like Google, Medchemicum, and it's a really great opportunity for us to collaborate with David and to apply his technology to our space. What's about ChemSpace? So ChemSpace, a company which was founded in 2015. Headquarters is located in Kyiv, Ukraine. We have shipping hubs in the United States and in Europe as well. We operate under two business models. So the first one is we're working as a discovery CRO, helping our customers to enable drug discovery projects, mostly early stages like hit identification, hit expansion, and SAR studies, and a little bit later stages like lead generation and lead optimization. Another business which we run, we operate as an online platform for sourcing, purchasing small molecules and biologics. We build customizable solutions for our customers to simplify the purchasing process of small molecules for their discovery projects. Okay, and let's talk about ML-assisted space generation. So it's not a kind of big news for everyone that combinatorial chemical spaces are in use in drug discovery. These spaces could be source of new starting points for discovery projects. It's a great sources to perform heat expansion, SAR studies as well. There are a number of spaces, commercial combinatorial spaces available on the market, and they differ from each other based on the space they cover, the collection of building blocks which were used to generate these spaces. But what is common for all these spaces is they are combinatorial. The most explored chemical space, I would say, enamine real, and there are numerous publications where enamine real compounds were used for drug discovery projects for hit identification and expansion. When we're talking about combinatorial spaces, it's important. The most important aspect, I would say, it's the synthesability of the final molecules. And if we do not address the synthesability of the molecules while space generation, we may face potential problems like low yield or some problems upon purification. Or in some cases, we can not even get the final molecule at all. And of course, there are some solutions how we could address synthesability. The first solution is to perform experimental validation of the reagent. And I would say it's the most reliable approach how we can get this space of synthetically accessible molecules. This approach requires some investments, of course, to buy reagents, to set up these experiments. And once again, it still limits to the collection of building blocks, which we experimentally validate. Another approach is to use a computer-assisted synthetic prediction models. So basically, we could predict, for example, yield for the molecules we generate, and it's a good approach. And there are reported results in the publication when it works, and the synthetic yield is predicted quite accurately. But using this approach, we still need the full molecules to be enumerated. And it limits us, if we're talking about or thinking about to generate the space with like 100 of billions molecules. So that's why our solution is to address synthesability on the building block level. So basically, to apply the machine learning on the stage when we select building blocks for space generation. When it comes to machine learning, we need to be very cautious with the training data sets. We need to be sure that we use reliable experimental data. And we are lucky because due to our collaboration with Enamine and years of expertise of Enamine in the synthesis, we got this very reliable training data sets. So basically what they provide us the statistics for the reagents they used to build Enamine real. The size of the training data sets varied from 1,000 data points to 20,000 data points, which is more than enough to train good models which could then generalize information for the huge collection of building blocks. So the format we got the training data was like this. So for each reagents we got the kind of the classification, if it's good model or good building block, sorry, or if it's bad building block. The assessment was done based on the performance of this building block in a particular reaction. For example, this carboxylic acid was kind of successfully used in 18 setups, and successfulness here means that the product final product was synthesized and purified. And just in 2 cases, this reagent failed. So that's why it's qualified as good. And for example, this reagent, Enamine did like 22 reaction setups with this reagent, and just in 1 case, the final product was successfully obtained. So, and it means that the reagent was qualified as bad. What is also interesting detail, which we would like to draw your attention to, is that we used 2 representations of molecules of the building blocks as an input for our graph neural network. First of all, we generated syntons. So we replaced the reaction handle with kind of dummy atom. But we also used a second representation, which corresponds to full structure of the building blocks. And this is important because here you can see like 3 building blocks, and 2 of them, they're good, 1 of them bad. If we generate the syntons for these 3 building blocks, we get the same synton. But at the same time, 1 of them was qualified as bad. And it means that probably this particular halogen, like fluorine, wasn't good for the particular reaction. So having an input, these 2 representations allow us to add this information and allow model to learn which kind of replacement should be here. Okay, so this is a general workflow, how we suggest to generate this specs. We start with a collection of building blocks. So it could be commercially available building blocks. It's actually what we used for the freedom space. It could be a proprietary collection. The next step is to create so-called building block pools, basically qualify the building blocks which will be suitable for the particular reaction. We do it using a set of smarts and basically ensure that the building blocks in the pool contain the needed functional group to participate in this or that reaction. The next step is apply our machine learning models to filter out potentially unsuccessful reagents. So far, we have models trained and ready to use for 40 reaction protocols, and these protocols include 2 and 3 component reactions. So here you can see the examples of the reactions. Once again, we make sure to include the most common reactions in drug discovery. And finally, we can proceed with enumeration using the potentially successful building blocks. So this is just an example, for example, amide coupling. So we have, let's say, the collection commercially available building blocks. Applying our set of smarts, we can get this building block pools, so basically the set of amines and the set of acids. Then we do filtering, so we apply the separate models to filter out potentially unsuccessful amines, and here we use another model to filter out potentially unsuccessful acids, and ended up with a kind of refined pools of building blocks. And then we could proceed with enumeration and get the final set of molecules. This is ML filtering. ML-based filtering was actually applied for generation freedom space 3.0, like the previous version, and it was done like almost a year ago. And while this time we were able to analyze the synthesability actually of these molecules and reliability of our approach for space generation. And here you can see the results. The success rate, the synthetic success rate for 10 set of molecules, like different size. But on average, across these 10 sets of compounds, we can observe like 80%, more than 80% on average success rate, which is good. And we also analyzed the order fulfillment. So basically, the milestone 1 starts once we get the list of molecules from the customer. Then while this milestone 1, we source the starting reagents from the vendors, from the suppliers. And starting from milestone 2, we start the synthesis. And you can see here that within like 2.5 weeks, we could get like from 80% in this case to 70% in this case, molecules already synthesized. Using this approach, using kind of being sure that the space we will generate contain synthetically accessible molecules, we generated Freedom Space 4.0, and we used all 40 reactions protocols. We have machine learning models trained. We used 72,000 building blocks provided by 16 trusted suppliers. We selected the suppliers because we work with the suppliers doing our platform catalog business, so we know how quickly they can deliver these building blocks. We also applied a cutoff based on the price to select this pool of 72,000 building blocks. So, and we expect the success rate for these freedom molecules over 80%, as we kind of experimentally proved for Freedom Space 3.0. The lead time for these molecules will be between 4 and 6 weeks. So the size of the Freedom Space 4.0 is 142 billion molecules. And this space is available just as a Synton space. For your convenience, we also enumerated 2 subsets from this space, Synton space. The first subset contains 20 billion molecules, and these molecules meet the criteria rule of 5. Seeing the demand among the customers for larger molecules, the molecules beyond a rule of 5, to address more challenging targets, PPI interactions, also proteins which have like shallow surface pockets. We also enumerated the second subset, which is called beyond the rule of 5 enumerated subset, which is 68 billion molecules. So how you can get access to the Freedom Space 4.0? The first way, you can download the enumerated subsets, rule of 5 and beyond rule of 5, using FTP. So the information is actually available on our site. You can do it easily. The second way to work with the Freedom Space 4.0 is to run the searches using different tools. For example, biosulfite Infinity, so Freedom Space is accessible through Infinity, Aliferon Hyperspace as well, and of course RTKit. And David will talk about this option today a lot. Actually, to enable the RTKit search, you need to have access to raw symptoms and reaction file. And we also provide you with access to this information. What you need to do, you need just to contact us. We need to sign licensing agreement, and we provide this data for free. This is overview of like physiochemical properties. You can see that the space contains like rule of 5, beyond rule of 5 molecules. And this is a workflow, how we envision synthesis of these molecules, because it's not, once you use the Freedom Space compounds for your discovery purposes, eventually you will need to synthesize some of them. So once we get the list of molecules from the customers, so what we do, we map back these molecules to the starting building blocks, and we source these building blocks from the vendors. We deliver them to our partners to Enamine Germany, and they proceed with the synthesis and purification. Basically, once it's done, the compounds will be shipped to you to proceed with biological assessment. We offer quite flexible pricing model. So basically, the more you order, the better price you can get. And I also would like to mention that this building block pre-filtering, like prior enumeration, can be applied to any building block collection. It means that if you have a proprietary in-house collection of building blocks, using our approach, you can easily generate custom proprietary space which you can use for your discovery purposes. So the workflow are going to be the same. So you provide us with your proprietary collection. We will prepare the building block pools using our set of smarts, and then we do filter on building blocks with our machine learning models. And on this stage, space generation, we offer like two options. Option one, it's a general space when we use just as a proprietary building blocks, just your collection of building blocks. And the option two is expanded space, where we can use as an addition another collection of building blocks, for example, Enamine real collection. And we make sure that the final molecules we generate on this stage will contain at least one building block from your proprietary collection. So the next step is to perform property filtering. So for if customers provide us with some criteria, what kind of final molecules they are interested to have in the final space, we can address it. And of course, we could support and do the updates of these custom spaces. This is basically all from my side. I hope that I persuade you that the space we generated, Freedom Space 4.0, contains molecules which could be synthesized with 80% success rate, which is good. And I encourage you to use the Freedom Space 4.0 for your discovery purposes. But what is also important that since the size of the space is quite huge, we need like a special approaches how to explore these spaces. And with that, I would like to pass the stage to David, and he will talk about the possibilities, how we can explore such spaces as Freedom Space.
Okay, thank you very much, Olga. I will just attempt to share my screen. Hopefully that's okay. It's about 5 years or so since I last gave a webinar, so I'm rusty, but anyway, here we go. I've been working for the last few months on tools within the RD kit to search synthon spaces, which clearly Freedom Space is a key example. There's already in the RD kit a preliminary implementation of the work I'm going to talk about today, which is based on an algorithm that Liphart and Sander published a year or so ago. I tested it on Freedom Space 3.0, which has just been mentioned was about 7 billion compounds, and it worked pretty well. But when I was given the access to 4.0 just after Christmas, with its about 2 orders of magnitude more compounds, it blew up completely, couldn't be handled at all. So I spent the last month or so making it more efficient, both in CPU time and in memory. Crucially, the memory was a real issue. And so what I'm going to talk about today should be available in the next release of the RD kit, which is scheduled to be on the 31st of March this year. So yeah, and it should be said that the code is still under active development, and so we're currently labeling it experimental, and the API and the results may change as we do more testing, but I think it's pretty stable at the moment, and the code's currently under review before being accepted into the master branch of the RD kit, ready for release in a couple of weeks' time. So what it can enable you to do is to search both by substructure or fingerprint similarity into the space, and currently on my Mac Mini, I've got a Mac Mini M4 Pro with 64 gigabytes of RAM. So all the timings you'll see below are based on that. And the Freedom Space, you can search it in about 4 gigabytes of RAM, and a simple substructure search takes comfortably less than a second. So I think it's perfectly feasible to search it on a laptop, on a fairly routine laptop. Certainly my 3-year-old MacBook Pro can do it. So I'll just run you through the basic algorithm, which, as I say, is based on the work of Lippard and Sander. And basically, you take your query molecule, and it's clearly infeasible to do an enumerated search or search the enumerated library. So we chop the molecule up into fragment sets based on any number of bonds to produce the right number of fragments. So in this case, in Freedom Space, there's no more than 3 synthon reactions. So it'll produce all sets of fragments, 1, 2, and 3 fragments in size. So for example, in this molecule, it might cut across here and produce these 2 fragments. And then in this little amide building reagent set, we've got these synthons representing the acid, these representing the amine, and so it matches this fragment against this set of synthons, and it finds that's a hit, and that's a hit. It matches this fragment against this set of synthons and finds that's a hit, and so it builds the 2 molecules, bolts the 2 synthons together, and then you see your hits at the end. And that's a much more efficient way of doing the search. And when it's done the final hits, it does do a final sanity check. It runs the whole query against the whole hit just to make sure that in the process of fragmentation and rebuilding, it hasn't lost some information. That's more of an issue with fingerprint searching than with substructure searching. So the database, you need to pre-process the database to search it at these sorts of speeds. So as Olga mentioned, you get the Synthon database from them. It's in ASCII format with smile strings and details of which synthons are used in which reactions. And then you need to process that to make a binary database that's then searchable. That takes about 15 minutes for Freedom Space, and it produces a file that's about half a gigabyte in size. And this is the commands you'd use. You need to make one database file for each fingerprint type. That's quite important. I'll go into that a bit later on. Processing Enamine real, which I don't have the 2.7 trillion molecule version, which was a bit of a surprise to me. Mine's only 72 billion. In total, and that takes about 2 hours to generate the database. And the key reason for that is there are many more reactions in there, and it's actually the number of reactions that takes the time. It's generating lots of fingerprints and doing quite a lot of pre-processing as it goes along, just to make the search as fast as possible. So despite being old and experienced, I shall attempt to do a live demo of this in the notebook. It's not something I usually do, but anyway, we'll give it a go. It worked before. So having produced the database using a command like this is based using the RDKit fingerprint type, which is a path-based fingerprint similar to the original daylight fingerprints that some of you may have seen in the past. So reading the database file, you can do it on multiple threads, and it takes less than a second. There it is. And according to me, there's 42 reactions and 141,966,000,000 possible products, which is pretty impressive, I think. So if I'm going to query it with this molecule, you read the molecule as a smarts. It's pretty important that you interpret it as smarts rather than smiles. You can read in a model block that's been created using ChemDraw or Marvin or a sketcher like that to do a query. Those also work. So looking for this molecule within the freedom space. You can see it took a quarter of a second and it's produced 47 hits. But you notice if you look at them, they're actually pairs of molecules. So I'm showing the first 6 hits and the last 6 hits in the hit list, and I restricted the number of hits to 1,000, which is the default for this. Clearly, in this case, there are only 47, so that's not an issue. And you'll notice that these pairs, obviously, a synthon, as Olga described, isn't a reagent. It's a theoretical construct, and there's clearly, I remember from my days studying chemistry, many ways of making an amide. And so these are two. The last bit of the name of the molecule at the bottom is the reaction that was used, and you can see these are 2 different reactions using the same synthon to produce the same hit. But you can see it's quite clearly a hit. There's the query. There's the match going down through there and round there onto that ring. So you can also do generalized substructure searching. Greg Landrum, the RD kit man, has a blog post about this, which he updated a couple of weeks ago. So this is using a molebot that's been created using Marvin. You have to do a bit of extra setups at the end here. So I'll make this notebook available via Olga after this webinar, I guess, so that all the code you need to do the searching is available for you to try. So that mole block represents this search, which is this 6,5 heterocycle, any aryl ring on there, and a chain of 1 to 3 carbons here. And I'll just do that search. It takes, sorry, I'll do that first, and then I'll do this search. And it takes a few seconds. And the reason it takes a few seconds is it's not doing anything particularly clever under the hood. It's enumerating all possibilities of this molecule, including tautomers across, in fact, all 3 of these nitrogens. I think it generates tautomers. That's just using the RD kit standard tool. And there are no hits. And this is an issue that I don't know how to address. But is it really no hits, or is the software failing? And obviously, the real test is to enumerate all the molecules and run it and see. And that can't be done really. So I will say Greg ran this query against Kemble, and there were 2 molecules hit. So I'm guessing probably genuinely there's nothing in the freedom space that looks like that, and perhaps Olga might have some insight about that afterwards. She might know the 142 billion off by heart, for all I know. But just to prove that the generic searching will produce hits, this is another one. The input now is a SDX Smarts, which is the Chemaxon extensions to Smarts. It's not drawn particularly well here, but what it's saying is we've got this 6,5 heterocycle. This is a variable substituent, a carbon attached at this point, and it's attached to either of these nitrogens. So it's a small variation in the search. And if I load that up and run it, again, it takes a very short length of time, and these are the hits it produces. And you can see it's top 1,000 hits. There's many of these structures in the database. They're all the hits it's showing here have the carbon coming off the same nitrogen, the one that's opposite the pyridyl nitrogen. But that's just to show it can be done. You can also do fingerprint searching, and so as my example here, I'm using this compound, which is Tagrisso or osimertinib, which is something I was prolifically involved in at AstraZeneca. It's a treatment for non-small cell lung cancer. So here to do the search, you need to generate the you need to provide the fingerprint generator for the search. That needs to be the same one that was used to generate the synthon, the database to start with. It will spit an error message out, and I'll show you below if that's not the case. And this is slightly slower. Takes a few seconds to run, but it's pulled back. Nothing particularly similar to this one in the first 1,000 hits. The Tanimoto similarity 0.56 isn't great, and I think you would agree the molecules aren't particularly similar to it either, but that's how it goes. So it's important to mention that these aren't the best 1,000 hits it could find in the space. These are the first it finds in its search. There are more similar compounds in this database, I do know that. And I know that because you can also ask for a random sample of the hits. So 1,000 random hits from the possibilities. And if you run that, it takes a similar length of time. And you can see, this one is Hanamoto 0.78 with the original search. So if you just want to get a quick idea of what's in the database, and that's probably a good way of doing it. It gives you a good representative sample of all the possible hits you might find, and then you can put the extra time into running an exhaustive search, which obviously will take more than a few seconds. But you can set the maximum number of hits to -1, which means no cutoff, and then you'll see how big your RAM is really, because you might get lots and lots of hits. But that's the fingerprint searching. So as I said, if you try and do it with an incompatible fingerprint generator, so here's the Morgan makes Morgan fingerprints, and this same space that was created with RDKit fingerprints, then you get an error message, and you can ask the Synthon space what fingerprints were used, and you get this rather impenetrable string of a description of how it was done. And Greg has promised me that he will write something that will turn that into the right sort of fingerprint generator, so that if you lose track of what of how your space was made, your database file was made, then you'll be able to go back and use this to start searching again. So that's the just a quick run through of the capabilities at the moment. There's a number of parameters you can fiddle with to change the similarity cutoffs for fingerprint searching, that sort of thing. But it's fundamentally usable at the moment, and hopefully it'll be of some use to you doing these things. And it's applicable. I've only tried it on Freedom Space and Enamine Real, but it's in principle applicable to any fingerprint, any Synthon space that you can get hold of from other folk. So what's next is, I believe that this algorithm is amenable to 3D shape searching, and in the RD kit in the last release, it now incorporates PubChem's ROX type shape searching code. So I have some time, some funding to explore how possible that will be. I think it's pretty safe to say it's not going to take seconds to do the search. It will require a rather more hefty machine. So that's what's coming next. I shall hopefully start working on that next week. Next week. So just to say that we have a discussions board on GitHub for the RD kit. If you want to see additional features or report bugs or ask questions, then feel free to do so on there. It's a pretty active community. People will help. If you particularly want to want big things added, then funding helps, certainly. And I'm quite happy to, if anyone wants to assist with funding further developments, that would be great. So I'll just finish by thanking Greg, who does a great job looking after the RD kit. And I mentioned to him about November last year that I was between contracts, and if he needed anything, any small bits and pieces sorting out, then I was available to go do a bit of help. And he pointed me at this thing, and then rather splendidly introduced me to Andy Palmer at Coalabs, who is a venture capital company in the States, who very generously funded this work on a philanthropic basis, essentially from their point of view. So great thanks to him. And also thanks to Olga and co at ChemSpace, and also the people at Enamine, who've been very helpful providing me with data and early access to their databases, so I can get this organised in time for their release. Almost. It's a bit late, but it's almost in time for their release. And with that, I'll draw to a close. Thanks very much.
Thank you very much, Ned. Thank you. We actually admire what you are doing because it's important, and we're not just kind of testing this search or kind of for you. We also already use this search for our discovery project, and we may say it works. We were able to find quite good analogs to enable heat expansion in the SAR stages. And it's also it's great to hear that the next stage is actually a 3D search. It's something which we're still missing, I would say, to enable like 3D search in such a huge chemical spaces like fastly and then expensively. Okay, so I think it's a time for Q&A session, and please go ahead and type your questions in the Q&A section on Zoom. So far, like while we're waiting for some questions to appear, I would like to say that please contact us. You can find information how to contact us on our webpage. Request the sentence files and reaction files, and there also a link which leads you to RDGit library, and you can enable this search. Yeah, I think it's a really great tool to search exact match, and also to run exact match substructure and similarity. The first question, do we need to pay for the freedom syntons? The answer is no. But we need to sign a licensing agreement. So we will provide you with a template, and then you can basically sign it and get the syntons for Freedom Space for free. So we are very interested, and we are encouraging people to use this space to use RDKit search. There is development and run it within Freedom Space. As the next question, how client proceeded parallel search queries? I think this is question for David. David, how if it's possible to proceed with parallel search queries?
Yes, so the searches I showed were using a threaded search on a single CPU. So I was using 13 threads on that. It's not possible to parallelize across computers at the moment, and I suspect for this work that's not really necessary. It's fast enough. It might be possible. It might be necessary for the 3D search if I can make that work. But at the moment, it's just using the C++ threading within the executable, if that answers the question.
Yeah, thank you very much. The next question, how does the Freedom Space compare to Enamine Real? Does it have certain advantages for certain applications in drug discovery? Thank you very much for the question. We used, first of all, a different collection of building block, commercially available building block from different vendors to generate the Freedom Space 4.0. The overlap between Enamine's real space, 70 billion molecules, and Freedom Space 4.0 is less than 3.6%. So basically, we can say that this is a unique space. It's different from real. And I would say that it's kind of they could become they could add to each other, let's say. So it makes sense to run the search like within real and within freedom. Yeah, regarding certain advantages for certain applications, yeah, first of all, freedom space contains more molecules like beyond rule of five. So if you're working with like challenging targets, targets with shallow pockets, surface pockets, so it's a good opportunity to use freedom space. Once again, certain advantages. So this is a different, basically different spaces. Yeah, and I would consider like both spaces, and in one of them you will definitely find something helpful, something useful for your discovery projects. What is the overlap between Enamine real and freedom space? Yeah, I answered this question, 3.6%, which is quite small. What are possible subsets of compounds this freedom space fall into? Yes, so I mentioned that the whole size of the freedom space is 142 billions of molecules. And this space contains different molecules from molecules with molecular weight like 300, 350 up to almost 1,000. We do have two enumerated subsets like within rule of five, which may say kind of drug-like molecules and molecules like beyond rule of five. Yeah.
Could I just make a comment there?
Yeah.
It occurs to me it would be quite trivial to put filters on the search for molecular weight, for example, or number of atoms. If anyone would think that would be useful, that would be absolutely trivial thing to do. So I'll put that in quite soon. Okay. Yeah. If that would help.
Yeah, I think yes. The next question, I don't know how to program. Can you access the search from some web page? This is a good question, and actually this is something we would like to enable. So we were thinking to prepare like a web page actually and enable this type of search that presented today for freedom molecules, for freedom compounds. Yeah, we will do the announcement. Yeah, I believe that this web page will be available like in a few months. The majority of molecules contains which set of compounds? Yeah, I think you may have a look at the distribution of the physiochemical properties and basically understand that I would say that the majority of compounds from the freedom space are within like 500, like 700 Daltons, if we're talking about molecular weight, like it's majority of molecules for freedom space 4.0. Another question, adding filters would be super useful. I think that you may kind of comment, as far as I understood, filters, I mean, we can kind of guide the search and do some setup while doing the search. Is it correct?
Yes, it would be quite easy to put a parameter at the start of the search to limit the hits you would get out to particular ranges of molecular weight or whatever. It would speed it up, I guess, apart from anything else. So, could be useful. Yeah, and certainly would be very easy to do. Yeah. I'll make sure it's in the release.
Yeah. And probably the last question, what percentage of 142 billion molecules are Rule of 5 compliant? 20 billion molecules. Yeah, I think we're done with the questions. Thank you very much, everyone, for attending the webinar, for listening to us, for asking the questions, and it was a great pleasure to host today's webinar. Please, if you have follow-up questions, if you need some additional information, please contact us, contact me, David. And as I said, this webinar will be accessible on our YouTube channel. Thank you very much. Have a nice day, everyone.